Hi, welcome to this session. My name is Madhav Sathe. I'm a platform architect at VMware. I'm really excited to talk about building reliable streaming pipelines using Reactor RabbitMQ Streams. We are introducing a new API here. It is called Reactor RabbitMQ Streams. It is currently in alpha. It is an open source streaming API used based on Reactor RabbitMQ and Project Reactor. The API embraces reactive and functional style of coding. Before we start showing sample, let us first understand the top capabilities needed to build streaming applications. First, developers need an ability to efficiently stream in and out business objects rather than dealing with messages or byte arrays. Enterprises want to use schemas as contract between publishers and consumers and potentially use a centralized schema registry as well. No enterprise likes to lose messages in the pipeline. Delivery guarantees are crucial both for publishers and consumers of the event. Essentially, the pipelines need to be reliable. When it comes to distributed systems, you always have to take failures into account. The API should be resilient to failures. And finally, you are streaming events to apply some kind of transformations. So you need operators to help you achieve grouping, windowing, aggregations, and so on. Most important value proposition of Reactor RabbitMQ Streams is that it abstracts away the complexity. Developers get simple to use and declarative API to rapidly build reliable and efficient streams. Now let us take a look at reference pipeline. We'll dig deep into the code. The Git repo for this demo is shown over here. The pipeline has a producer application that publishes stream of Avro objects called myNumber. These events are sent to myNumber exchange of type fanout. This exchange has myNumber queue bound to it. The multiplier application here demonstrates a typical event processing application. It receives input event, applies transformation, and sends the transformed event to a sync system. In this case, the sync is essentially a multiplied myNumber exchange. In this sample, we will learn how to use auto configuration abstraction built specifically for Spring Boot. We'll see how to create RabbitMQ topology via code. We'll use strongly typed streams, Avro for management of schema for business objects, and transaction semantics across distributed systems. The application YAML shown here has connection details for RabbitMQ endpoints. You can declare more than one endpoints and pick one of them as a default. Reactor RabbitMQ Streams AutoConfigure library automatically populates the application context of this Spring with an instance of Rabbit endpoint service. In this case, the Rabbit endpoint service bean points to the standalone endpoint. First, we will define the topology. The details of the topology configuration are in a bean of type consumer of topology builder. We'll use Rabbit endpoint service to declare topology provided in this bean and print it. In some organizations, roles are separated between RabbitMQ operator and application developers. Having topology managed as a separate code helps in separating these roles as well. Here you can see that the topology configuration is defined as a bean of type consumer of topology builder. The topology builder API is used to declare exchanges, queues, and their bindings. For this pipeline, we don't really need any policies, but you can also declare policies if needed. For instance, you can add an alternate exchange and its queue to handle unroutable events. In the streaming application, we won't actually create the topology. Instead, we will verify that the topology exists. We use declare topology passively function for that. Although you can very well declare the topology as part of the streaming application if needed. Then we create a strongly typed producer stream of type myNumber. We will see how Avro is used to manage the schema of myNumber. We then route the producer stream to desired exchange. We also have added some retry conditions as you can see here. Then we can send the myNumber objects from the flux, which produces the flux of sent events. We don't really care at this point how the flux of myNumber is created. Finally, we need to subscribe. Without that, there is really no action. Block last here subscribes and blocks indefinitely until the upstream signals its last value or completes. Now let us understand how producer stream uses Avro. Avro relies on schemas which are written in JSON. In this case, the schema for myNumber is available in the local file system. The Avro Maven plugin builds a Java class for the schema and creates myNumber class. We create strongly typed producer stream using this class, which sends the messages using content type as shown here, myNumber plus Avro. For consumer code, we will first create a transactional consumer stream. As you can see, this too is a strongly typed stream. The consumer stream points to the myNumber queue. Here we see that we have defined prefetch and act configuration as well. Then we receive the business events in the flux of transaction of myNumber. Here, the business events, that is myNumber, is actually encapsulated in transaction. Now let us understand how consumer uses Avro. Here, the consumer application has the myNumber schema in its local file system. The consumer stream receives messages with content type, myNumber plus Avro. It tries to find a matching schema in the local schema registry. It finds matching schema with a MIME type, myNumber plus Avro. This is how Avro deserializes the messages into myNumber. You can also use a centralized schema registry. The API will find matching schema on the registry. Again, matching content type of the messages to the MIME type of the schema on the registry. Reactor RabbitMQ Streams API supports schema evolution as well. There are plenty of samples available in the reference guide. After the event is received, we process it and transform it into another type. In our case, the process event is of type multiplied myNumber. This too is managed by Avro schema. The transaction type has a map operator that helps transform input type to output type and pass on the transaction context of the input event to the transformed event. The result is a flux of transactions of multiplied myNumber. Now we want to persist the transformed event. We create a strongly typed transactional producer stream of type multiplied myNumber. We route it to the destination exchange we already created, and we send the flux of transaction of multiplied myNumber. The delay is added over here for demonstration purpose only. What we get in the end is a stream of sent multiplied myNumber events. Again, so far, this pipeline has only declared its intent. As this is a reactive pipeline, nothing really gets done until subscribe is called. In the end, we commit the transactions on the strain stream via subscribe. Now let us understand how this commit ensures delivery guarantee across distributed systems. What we want to ensure is that myNumber queue deletes the event only when the pipeline has successfully consumed the event, processed it, and persisted the processed event. First, the multiplier application receives First, the multiplier application receives an event from the source queue. The event is encapsulated in a transaction, as you can see here, thanks to the transactional consumer stream. The application processes and transforms the event to another type, but the transaction context is maintained during this mapping. The multiplied my number event is then published to the sync queue. The sync queue could be running on any RabbitMQ cluster. Upon receiving the publisher confirm from the sync queue, the stream actually carries out the commit process on the sent sent event stream basically, which then triggers commit and act on the original my number event. Now the pipeline can be certain that the input event is fully processed and it is safe to delete it from the source queue. Moreover, the acts are batched together for higher efficiency. This is an extremely powerful yet simple way of building highly reliable and efficient streaming applications. Now, let us take a look at demo.